Scope Public Lecture Series. Today's topic, The Invisible Universe and the Power of Citizen Science by Eleni Vardoulaki of the National Observatory of Athens. I'm your host, Dr. Frank Summers of the Office of Public Outreach here at the Space Telescope Science Institute. And as always, I want to thank the wonderful tech team, Gary Gilbert and Grant Justice, for recording this meeting and streaming it out to YouTube. Our upcoming talks on December 3rd, Gregory Sivakov from the University of Alberta in Canada will be talking about hunting the stellar undead. Yes, stars do die. And how do we find them? How do we find these stellar remnants? They have fantastic properties. So you'll want to hear about that in December. For 2025, all of 2025 is currently to be determined because, as it says here, due to funding changes, the public lectures will go on hiatus starting in January 2025. The funding streams that supported the public lecture series have now dried up and been switched to other projects, and we are in the process of searching for a new funding stream to support the public lectures. We will keep you updated. You can find out such information on our website, www.stsci.edu/public-lectures. And on there, you will find in the lower left links to our webcasts. There are, more than 100 different webcasts out there, both on our YouTube playlist and our webcast archives at STSCI. And in the lower right, the email, where you put in your email address, hit the subscribe button, and you'll get the monthly reminders and news about what our future will be. Also on the website are, of course, the lists of the lectures. And when you click on an individual lecture, you'll come up with all the information about it, including the abstract, as well as after it has been recorded, linked to the STSCI webcast and to the webcast on YouTube. For email, as I said, sign up for the announcements on our website, or you can also subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word. You will get new video notices and reminders of live events like this. Finally, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. Our social media, we run the social media accounts for the Hubble Space Telescope, the Webb Space Telescope, and the Space Telescope Science Institute on Facebook, X, YouTube, and Instagram at the handles listed there. So you can follow all the recent discoveries from our telescopes. Speaking of recent discoveries, the news from the universe for November 2024. Our story tonight, gorgeous eruptions from the R Aquarii system. So what is R Aquarii? Well, you've probably heard of the constellation of Aquarius, and R Aquarii is just this star down here in the part of Aquarius. It sort of looks like just an average, ordinary, nothing star. But I wouldn't be talking about it if it was a nothing star. It's an interesting system that has some very very interesting components. All right, so the first component is a red giant star. And I've put up here a diagram that shows you just how large a red giant star is compared to our sun. 50 to 100 times larger than the size of our sun. So that's kind of big. Second thing is this red giant is a variable star. So this is a video illustration of a variable star. And you'll notice that it swells in size and gets very brighter, and then it decreases in size and gets fainter. It gets brighter as it gets bigger and gets fainter as it gets smaller. All right, that's just an example of a variable star. For our Aquarii, we actually have a light curve. This is the measured light curve of its magnitude, and higher is brighter. And you can see that in about July of every year, our Aquarii reaches its maximum. And then about January of every year, it reaches its minimum brightness. And it goes up and down about a year, on order of a year. And so this is the pulsations that are happening within this variable star. Okay, so you've got a red giant that is variable, and the variability is actually quite large. It's like a factor of 500 to 700 in brightness. Okay, so it really gets much, much brighter and then much, much, much fainter. Okay. Second component is a white dwarf. Okay, we had a giant, now we've got a dwarf. That means this dwarf is really, really, really small. Matter of fact, we don't compare it to the size of the sun because the sun is much, much, much bigger than it. Instead, we compare it to Earth. A white dwarf is the mass of about our sun compressed down to the size of our Earth, which is huge. It makes it incredibly dense. Okay? This isn't a star. This is a remnant of a star. This is the dead piece of a star after the rest of it burns out. And the core of the star, okay, becomes incredibly compacted. It's like a giant ball of carbon. It's gone through all of its fusion, leaving behind carbon, and it's about the size of Earth, and it weighs about the mass of the sun. And we like to say that 1 tablespoon of a white dwarf would weigh a ton. All right. So here's the idea that's going on in the Araquari system. You've got this red giant that's pulsating bigger and smaller and bigger and smaller. Okay. And around it, you've got this white dwarf orbiting. It actually orbits in about 44 years. But it also is close enough to the red giant that its sun can suck material off of the red giant. That material spirals onto the white dwarf, and then the white dwarf either ejects it or explodes. There are some explosions on it, and that spews material out into space. These are these eruptions that I was talking about in Araquari. And so this happens periodically and continuously over the years. That stuff is spewing out from Araquari. And these gorgeous eruptions, when observed by Hubble, look like this. Yeah. Isn't that cool? This is great. Okay, so you can see marked by the diffraction spikes where Araquari is in the center. And the scale of this is like 2,500 times the scale of our solar system. Our solar system, the planets in the Kuiper Belt go out to about 100 AU in diameter, okay? The diameter here is 2,500 times larger. So you can see that material is being spewed out of this system and in a directional component, right? Because it's leaving behind these trails, and it's moving out at 1,000,000 miles per hour. So it's spewing out very far into interstellar space. And it's really kind of cool that you get this. But what's even cooler is this is not the first time that Hubble has observed it. All right, so we can go into this central region and take a look at how it has changed from 2014 to 2023. And so we put together this time-lapse movie, and here. And in this time lapse, you can actually see material moving away from Araquari. You can actually see the changes, the stuff spewing out and making new stuff. I'm going to play that again because I just think this is great. This is just wonderful, right? You can actually watch things change on a human timescale. There's not many things in astronomy where this is true. All right. And we get to see the material spewing out from Araquari. All right. And you can see on a larger scale where that material has gone over many, many decades. Okay. And so these are the gorgeous eruptions from Araquari that are referred to in the title. All right. Our speaker tonight, let me stop. Our speaker tonight is Eleni Vardoulaki from the National Observatory of Athens. And she got her PhD at the University of Oxford in England, where she studied radio astronomy and active galaxies, a wonderful topic. She then did postdoctoral positions in several places around Europe. She went to Portugal, Crete, and 8 years in Germany, you said. So that's quite the traveler on your postdoctoral phase, but she's finally returned home. She's back in Athens where she was born, she tells me. And she has a job like me, being an astronomer who explains things to the public. She's involved in public outreach at the National Observatory. And she, one of her big projects that she works on. She is the co-eye of the Radio Galaxy Zoo that she'll tell you about in her talk today. She says that she spends her time often as the mother of a 12-year-old, because that takes quite some effort. And she loves nature, photography, and painting. So, ladies and gentlemen, Dr. Eleni Vardoulaki.
Thank you very much for the great introduction. Right, let's try to do this and share. Right, I have very nice things to explain to you today about the invisible universe. Please let me know if you can see this and it works.
It's looking great. Thank you.
That's great. That's what I want to hear. So I will talk to you about the invisible universe and about citizen science. For us, it's very important that the citizen scientists get involved into research and help us do research in a better way. So I will start with a story of how our universe was born and how we observe it. I want you to imagine that you are inside a dark room, that you try to see a little bit of light, but you can't see anything. You open your eyes more and more to get a glimpse of light and you cannot see anything. Imagine that this is the early universe. It was like a dark room where light could not be seen. Matter was there, but matter was not interacting with each other. And then something happened and someone opened the lights. To get to that stage, we need to go a bit further back at the beginning of the universe and how we believe it began. So our story begins 13.8 billion years ago when from a singularity, time and space was created and the universe started growing very big and very fast in a time that we call inflation. And because, as you will understand, I like analogies and chocolate, this is how we will describe the inflation of the early universe. If the early universe was a chocolate, this is my favorite Greek chocolate, then it grew very big, 10 to the 26 chocolates. This is a huge volume which we cannot comprehend. And this happened in a very small amount of time, 10 to the minus 13 seconds. It's not conceivable by a human how small this amount of time is. Maybe if you have children, you can understand. This is how much time you have left for yourself. But it's so small, we cannot even compare it to how long it takes for us to blink our eyes, which is 0.23 seconds. So this is when the universe started growing, space was created, time was created. And for me, the only analogy I can give you for the creation of the universe is the creation of a fetus. It gets created by a singularity, let's say, and space and its own time start to run after it gets created, and it grows and grows and grows. The early universe was very hot. It was a few million degrees, and matter was just being created. But as we said, it didn't interact with each other. We have the creation of the ingredients of what an atom will be later on. But because we don't have the atom yet, we can't see. We are still in that dark room. And imagine that the universe keeps growing, right? Imagine it as a balloon, and the universe is the surface of a balloon. And as you blow the balloon to grow bigger, the universe cools down and cools down. And eventually, matter starts interacting. You have protons and electrons interacting, and you have the creation of these bubbles, and the universe becomes visible to us. Of course, these are artist impressions, what I show you. We have the creation of the first stars and the first galaxies. And how? But, okay, before we know how, This took a long time for the universe to become visible. It took 380,000 years after the Big Bang for us to be able to see the universe with our telescopes. We first observed it in 1965 with a radio antenna, which gave Penzias and Wilson the Nobel Prize in Physics in 1974. And then we have been observing the cosmic microwave background radiation with telescopes in space. And this is the echo of the Big Bang, what created our universe. As I said, the universe was very hot, and as it expanded, it cooled down. And today, this radiation, the cosmic microwave background, is very cold. The temperature is minus 273 degrees Celsius or 2.7 Kelvin. And as I said, things starting to be created. Of course, you have hydrogen, the first atom, the simplest atom, and you start creating masses of matter. They attract each other because mass has gravity. The more gravity, the more it attracts other masses. It builds rocks. These rocks attract each other. Eventually, you will build a structure that will have enough mass that nuclear reactions start happening. These are the first generation of stars, and they start burning hydrogen into helium. But they could not hold the coherence as stars do in the third generation that we are now. They blow up very fast, and then new stars are being created from these stars. So what happens in the early universe? These stars create the first galaxies, and of course stars get created from cold dust. And the universe starts growing, galaxies start growing, stars being created from the materials of previously exploding stars. A very nice whole simulation. I think that's from you, Frank, of galaxies. Galaxies grow, they attract each other. Bigger galaxies attract small galaxies, or either, as we say, they cannibalize them. So we have a scenario of cosmic cannibalism. And as the bigger galaxies attract smaller galaxies, grow bigger and bigger and bigger, and we have the formation of big galaxies. They formed at the early universe 13 billion years ago, and we see them now in our local group, like our galaxy that is that old. So the universe goes, we come closer to the Earth, we come closer to our local group, which is composed of several galaxies. And the closest galaxy to us is the Andromeda Galaxy, of course, a spiral galaxy composed of stars, dust, and gas, and dark matter, which I will tell you about in a bit. And it has trillions of stars and a supermassive black hole in the center. And our galaxy, of course, that contains our solar system, okay, and our solar neighborhood with many stars. These are trails of stars around our solar neighborhood from observations from the Gaia satellite. And we're here in our solar system and our Earth. These are a lot of things that we know about our universe, but not everything, of course. We know many things about the observable universe because we made telescopes. We built telescopes and we were able to see them. But can we see everything about our universe? Is there an invisible universe? To answer this, we need to know the ingredients of our universe. So what is our universe made of? Our universe is, by a very small percent, is made out of visible matter, or we call it baryonic matter. This is 5% of the ingredients of our universe. The rest of it, the 95%, is dark. And it means that we cannot see it, with our telescopes, but we know it exists because we have these observations from the cosmic microwave background, and we have our theories and mathematics that tells us that there is something there, something else. And we see also the effects of this dark thing onto matter and onto the universe. The 27% is called dark matter. This is the biggest percentage of matter. It's dark, and it has a gravitational effect on matter. It attracts it. Okay. Imagine it as the invisible skeleton of our universe. Like our body is built upon our skeleton. Okay. In the same way, all the cosmic structures that we see in the universe, the galaxies, the clusters of galaxies, stars, etc., are built upon the cosmic web, this skeleton of the universe. But what is this 68% that is the biggest percentage of the universe? And it's a bit elusive. We have not observed it. We know that it exists because it has a very particular quality, let's say. It forces galaxies to go away from each other, right? So we know that the universe is expanding. We have observed it, and but this is happening in an accelerated way. So this is the role of dark energy. Dark energy is pushing the galaxies far away from each other, and it's in a hurry. It's like you're the driver, or dark energy is the driver of a car, and they are late and they want to go faster to their work, so they're pushing the gas pedal to go faster. And this is what it does to the universe. It pushes the galaxies further and further away, and eventually we won't be able to see any light from these galaxies. So the visible universe, we have observed it with many telescopes, more that you can depict here in this picture, from the Earth and from space, across the electromagnetic spectrum, from gamma rays and X-rays, the most energetic radiation, ultraviolet, visible, infrared, microwave, and radio, the less energetic. So the question is, can we see all these wavelengths with our eyes? Of course not. We can only see in the visible part of the electromagnetic spectrum. And this is because of our sun and mainly because of our atmosphere, because it is a filter. Of course, our atmosphere protects us from meteors and, asteroids and comets, and not so much asteroids, but yeah, from meteors, because they burn in the atmosphere. But it also protects from dangerous radiation from space, like X-rays and gamma rays, or from the sun, ultraviolet, or infrared radiation. It blocks a very big part of the electromagnetic spectrum, and that's why it's a very good planet to live in. In order to observe, because our atmosphere is thick, we need to build our telescopes high in mountaintops. The higher you are, the less layers you have of the atmosphere, so you see the universe clearer. Okay, but if you want to go to observe other parts of the electromagnetic spectrum, like the infrared, you either go to high mountaintops or high in the atmosphere, like with balloons in the stratosphere, for example, because, as we said, the atmosphere is a filter and it blocks a very big part of the infrared radiation. And if you want to observe the universe in the X-rays, you have to send telescopes in space, X-rays and gamma rays, because our atmosphere blocks completely this kind of radiation and makes it safe for us to live on Earth. For infrared, if you want to observe better, you send telescopes in space, but as we all know, it's very expensive and it takes many years to construct a very good telescope, like the James Webb Space Telescope, that, if I'm not mistaken, took 10 years and cost $10 billion. So it's not easy, but it's a fantastic instrument. And if you want to observe in the radio, of course, you can do it from the ground. You need big antennas, like the Very Large Array, the VLA in New Mexico. Maybe you know it from the movie context. Or antennas like the Low Frequency Array that is based in the Netherlands and in many countries around Europe that form a network between them. So this way you build a bigger telescope that can observe with higher sensitivity and high resolution the universe. And the technique is called interferometry. And sometimes you have natural valleys, like in China, and the FAST radio telescope, which is the biggest radio telescope in the world, 500 meters diameter. Or you build a telescope the size of the Earth, like with the Event Horizon telescope. And this way you can zoom into the center of galaxies and observe the supermassive black holes in the center of galaxies like M87 or the center of our galaxy. So let's see what we observe with different at different wavelengths. In the same way, like we see a human, with our eyes in the optical, we can see the hair, we can see the body, we can see the eyes, we can see the teeth, but we cannot see through the skin. We need to get an X-ray to see the bones. Similarly, when we observe a galaxy with different parts of the electromagnetic spectrum, in the optical, with our eyes, we see stars and we see dust. And actually, most of the light from the stars is blocked by this dust. We need to use the infrared to see through the dust, and we need to use X-rays, which we cannot see with our eyes, to see very energetic particles that come from the supermassive black hole. So we see different parts of the galaxy, and all these are important for us to understand how galaxies are formed and how they grow and how they evolve. I will stay on this picture in the infrared because when the first images from James Webb Space Telescope came out and we saw them in our TV screens and in our newspapers, we didn't realize that it's not possible for us to see infrared radiation. So what happens here? How is it possible that we can see this group of galaxies that interact with each other? I can see it with my eyes. So astronomers here use colors to color these images and they look like an optical image. This way, our brain perceives it as an optical image, and it's easier for us to understand it, not only as the public, but also for scientists to study this. So there is a very sophisticated way of coloring each wavelength at specific colors and giving it life. The same happens with X-rays. So this is an X-ray image of the Stefan quintet, the same interacting galaxies. What happens in the X-rays? We don't see it with our eyes. So with our telescope, we collect photons. The more photons you collect, the brighter it gets, your image gets. And then we create an image that we can see with our eyes, and then we can study it. But what happens if we cannot see it with our eyes and we want to make astronomy more accessible? So the last years, a fantastic technique emerged. It's called sonification, and it helps everyone see image of a celestial body of the sky with their eyes. So what happens in this sonification? Astronomers, musicians assign notes to the image, and depending on the size of the object or of the different morphology, it gets a different combination of notes, and it becomes a lovely musical creation. So I will play you a few sonifications so you see what I'm talking about. Let's hear another one. That is amazing, isn't it? It's the Carina Nebula with James Webb Space Telescope. Oh, it's playing again. Okay, I was surprised. It's amazing how the different shapes get different sounds. I love this one. Good. Let's see the next one. So this is the Crab Nebula. And if I'm not mistaken, is a composite image of X-rays, optical, and infrared. And that's my favorite. The standard field in X-rays. That's great. And this is supermassive black holes in X-rays. So I hope you enjoyed the significations. Now we're switching to the radio. If you add the radio into a game, you have the non-thermal part of the electromagnetic spectrum. You have objects like this one, which is an active galaxy. It's a composite image of a galaxy. You have the optical, the radio in purple, and the X-rays, hot dust emission. The radio part comes from different processes. It comes from high energetic electrons, high-speed electrons that interact with the magnetic field of a source, and they emit this synchrotron radiation, as we call it. And for us, astronomers, is a very important process to understand because these active galaxies affect a lot their host galaxy, the galaxy where they come from, and they affect their environment in general because galaxies live inside groups and clusters. So active galaxies affect their environment, they stop star formation, they do a lot of things. And it's very important for us to study these galaxies and understand them. A little simulation of what happens on the left when you have these energetic, high energetic electrons, high speed electrons interacting with the magnetic field. They emit in radio this blue light that you see, and they eject material at distances much bigger than the galaxy itself, and they hit their environment. Okay, and if you have a very good telescope like the EHT, as I said, you can zoom in into this supermassive black hole where everything starts and get an image of it. As you see here, you probably have seen this one before. This is from the center of our own Milky Way. It's Sagittarius A star, and it's matter circling around, plasma circling around the supermassive black hole. Right. Right, the radio. So you might be wondering what this is. Imagine that our eyes were radio antennas. This is how you would be able to see the night sky or the day sky, it doesn't matter, with our eyes, because with the radio antennas, we can see during the day and during the night. The atmosphere doesn't affect us. So you would see strings and filaments, you would see bubbles, you would see a lot of point-like things, sources, and they would be everywhere in the sky. But they come from different processes. Some of this emission comes from the center of galaxies, from matter around the black hole. As I said, you have these high energetic electrons, they interact with the magnetic field of the source, and they eject jets of emission, as in the simulation on the top right, and you get a real image of an active galaxy in blue, in radio. Or they come from other processes, which we call star formation. You also have similar processes, but further out, not in the center of galaxies. And these are caused by cosmic ray electrons. They interact with the magnetic field of the galaxy, and they emit radio emission. On the left is a simulation, on the right is a real image of a spiral galaxy and star-forming regions in orange. And this is dust, because to make stars, you need cold dust. So what do we need as astronomers, radio astronomers? We need to be able to understand which object comes from which process in order to study them and study galaxies. And in a small patch of sky, you have hundreds and thousands of these objects. The better your radio telescope is, the more objects you observe in a very small patch of sky. You have to be able to catalog them, you make catalogs out of them, to categorize them, to say if they come from processes of the supermassive black hole or they come from star formation. You have to measure how much energy they emit. You have to measure their size, etc. And this is a very complex process for astronomers because it takes a lot of time in order to do that. And you have to have many astronomers to look at the same region of sky because it's not easy. Some things are more straightforward. You can tell that a galaxy, you can tell that a radio source originates from the processes around a supermassive black hole because it has a very big shape. But sometimes you get very weird objects like bubbles. Usually bubbles are associated with supernova explosions, but sometimes they're not. And you call these odd radio circles, like on the top left, this turquoise bubble. Or you have some very weird wiggly jets that are related to two galaxies interacting and their jets are bending. So there is a whole zoo of structures and morphologies, and we need to be able to separate them and in order to study them properly. And that's why citizen science projects emerged. 10 years ago, the original Radio Galaxy Zoo started. The PI is Ivy Wong, and they classified 100,000 sources. So they gave to the general public the opportunity to help do science. They asked them to categorize these sources and identify the host galaxy from which it originates. And 10 years later, they are still using this data and they're training deep learning and machine learning algorithms to automatically classify big regions of the sky. More recently, the Radio Galaxy Zoo LOFAR classified 4 million sources in the North Sky. LOFAR, the low frequency array I showed you before, observed the north part of the sky, and had a lot of information in there. So it's not possible for a team of astronomers to visually inspect, as we say, to go and look one by one the sources, 4 million sources. We can't do that. We can get a small sample and then use it to classify the rest. And the project I'm involved in, I'm the co-I of the Radio Galaxy Zoo EMU. EMU stands for the Evolutionary Map of the Universe survey, which surveys the southern sky with ASKAP radio telescope. And our project was launched this summer. We are very proud of it. We have been building it for 3 years, and it will classify 40 million sources. And what do we ask? We ask for the public's help and to become citizen scientists, and help us also do discoveries, because the radio sky is full of objects that are unique. What do we want? We want you to go and look at the objects we have available for you, to find a radio source, to mark the host galaxy, where do you think the emission is coming from, and then classify them based on simple words, simple descriptive tags. So we are trying to build a bridge between astronomers and citizen scientists by creating a new language and not using astronomy jargon that is very hard to know. You need to know what it means, but also between scientists, this has become very difficult to communicate. And of course, we have an open communication channel where you can tell us about your discoveries, and discover the unexpected. Why do we want this? We will use this training sample from your data to train deep learning and machine learning algorithms. So then we can feed the algorithm with a huge part of the sky, and they will be able to classify very difficult objects. Of course, we have algorithms that can see a patch of sky and classify things that are symmetrical, like a circle or like an ellipse. This is easy. We can do it, but for more complicated things, the algorithms don't work properly yet. That's why we use training samples and machine learning algorithms, deep learning algorithms. This gets a bit more scientific, but I will say it in case someone is more interested in how we build it. As I said, it took us 3 years to build this experiment, and it was because we wanted to give the citizen scientists the best and most interesting targets to look at. Okay, as I said, a patch of sky, of radio sky, has a lot of information, and a lot of it is boring. It's not interesting. The shapes are circular. It's not interesting to look at when you want to do a discovery. And we want to enable discoveries here. So we use the technique that is called complexity. It's an algorithm that scans the radio sky, the paths that we gave, and it selects the most interesting regions, the ones that have the more information. That's why we have this example of the shot glass here. The one that is not fully mixed has the highest entropy, the highest complexity. This way, we selected the most interesting targets with the most interesting morphologies. And then for the dictionary that we made, the tags, we made a few experiments where we asked astronomers and the general public to describe these sources with simple words. How do they look like? Does it look like an hourglass? Does it look like it has a bridge between the two parts of the emission? So we used the natural language processing and created this simple descriptive tags that describe words we cannot decipher from simple algorithms. The goal is to use this eventually in the creation of science-ready catalogs And then when an astronomer wants to study objects that all have the shape of an hourglass or they all have tails, they can study it because they will be able to select the same things. And we have already tested this. So we have shown that there is a link between our descriptive tags and astronomical jargon. The SFG that is written there means star-forming galaxy. These galaxies that are forming stars, not the active ones. And if someone in the catalog that we provide goes and looks for traces host galaxy, it means that they are selecting the star-forming galaxies. Or they can try and look for rare sources, and they use a combination of tags, and they will find very rare sources that they can follow up with more observations. Finally, I'm very happy to announce that our project is available in 3 extra languages. So, of course, the original is the English. So we translated it in Greek, Chinese, and Urdu. And it's currently being translated in German, which will be up on the Zooniverse platform very soon. So scan the code, sign up, and discover the universe with us. Thank you very much.
All right. Thank you, Eleni. That was wonderful. You gave quite a overview of the universe and then really deep dives into selected parts of the universe. I especially appreciate your message that astronomy requires multi-wavelength observations to truly understand the objects out there. That seems to me one of the most important messages we can get out to the public. I'm sure you do that a lot in your work.
Yes, it's very important to use, for me in particular, for my science, there is no way I can study active galaxies with only one information, only one wavelength. It's a multi-wavelength science. And that's why we need different types of telescopes on Earth and space with different resolutions and sensitivities to get different processes. Yeah,
it's obviously we emphasize the visible light from Hubble versus the infrared from Webb, and often are showing the exact same object in the 2 different band passes, and you can see the contrast. One of the things that I found fascinating, because I hadn't really thought of this before, is that when we develop these citizen science projects, we of course have to train the people to observe them. But of course, in the last 6 to 8 years, artificial intelligence, in order to train a neural network, you have to provide all these examples.
Yeah.
So it sounds like what you're doing is you're giving all the citizen scientists the hard work. Okay, this is the stuff we can't really figure out, and we need you to do it for us, so then we can train the neural networks to be able to do it in the future.
Yes, it's very important. This step is the most important step in being able to do this in an automated way. We are doing it as astronomers. We're doing it in our, on our computers, but we need more eyes. We need more people to look at the same things to get a consensus of what it is, because some objects are very easy to understand what it is, and some are more complicated. And because we have done a lot of experiments, many teams have internal, sometimes we cannot agree between us what it is. If you have a team of 10 people, it's not enough to get a consensus. You need teams of thousands and tens of thousands to be able to do that. And this is how citizen science emerged. And it's actually very important step in understanding the universe and discovering new things. You will hear many times the discoveries by citizen scientists. Oh, they were looking at the patch of sky. Oh, look, a supernova that was not discovered before. Because for sometimes when you are an expert, you're a bit biased in what you see. But then when you have an enthusiast that maybe doesn't know all the physics, they they see details that you would not have noticed, and they find extraordinary things. And this is what we need.
Yeah. And I would just like to emphasize that some people think that, oh, if they're doing citizen science, you're just giving us the hack work. You aren't giving us anything important. But what you just presented here is that, no, the citizen sciences are doing the really important stuff because it can't be handled by computers. So this is stuff that really, they should feel that there's serious, they are doing some very serious work.
Yes, and I do hope that your viewers will go and take our project, and we try to, we have tutorials, and we try to explain the process. And for us, it's very important to have an open communication and help people. If they don't understand what the task is, we're more than happy to help. Or if someone wants to get involved on a higher level, maybe they're more familiar with this, they can join our team. We are more than happy. I'm recruiting.
All right. Well, Grant Justice has been watching the questions in the YouTube chat. Grant, why don't you turn on your video, come join us, and we will go through some of the questions we've got.
Absolutely. And I may need a little bit of your support on this. Unsurprisingly, our move to a different time slot has affected our questions from the audience as well.
It's all right. I suspected that an early start would bring in just not as many viewers live as we usually get.
All right, but I can start with this one, which I think
Yep.
will be interesting both to hear and for you to get to talk about a little bit more. Could you expand a little bit more on your sonifications? Is it comprised of specific scientific data, and what sort of added benefit does it bring to your work?
Okay. The sonifications was an example of how you can see the invisible universe, not see it, hear it. It's an attempt, and just to make clear, they're not my sonifications. These are sonifications by other people. I'm just sharing them here because I think it's very important to make astronomy more accessible, and this is a very big part of it. The first time I came across a sonification was through the pandemic. During the pandemic, we were doing an astronomy on tap online. So I was hosting this, and we had a guest who wrote a Python code to transform the image into a sonification. I'm sorry, I don't remember from the top of my head, but the idea is for our fellow people that cannot see with their eyes the images of the sky to be able to hear them. So you are opening up a new window for them to have, to be able to see the universe. And I think this is very important for us, especially the ones that do outreach like we do, because
Right.
listening, for me, it was amazing to listen to these images. I saw information that I thought I could see with my eyes, but I didn't realize I was seeing it, It made it more clear, it made it more vibrant. And if you close your eyes when you see, when you hear this sonification, it takes you to another level. It's amazing for me.
Yeah, I mean, the accessibility is extremely important, especially for the visually impaired community. But most of I think all of the ones you played were created by a group called System Sounds. And at a AAS meeting, I had Matt Russo from System Sounds join us for an evening talk. And he played, he hadn't done these ones yet, but these are accessibility oriented in terms of also, giving you an extra insight into it. But he also has done some that, like periodicities of planets around an exoplanets around another star. And when you listen to the thing, you get to hear the resonances between them that just watching it doesn't really quite give you. Okay, when you plug in, so he plugged in a couple extrasolar planetary systems, and you could really hear in the music the resonances that are there between the planetary orbits. So that was one that the data really, data analysis sort of came out sonically to it as well.
Yeah, that's
And
amazing.
I linked it in the chat for everyone who is watching online, but we had an entire program on it. And one of the things that was very interesting about sonification, like Frank said, is regardless of your ability to see or not, you can kind of start to understand the 3D space in which it exists, because it's not just random sound. It's not just picked arbitrarily, kind of like we do with JWST for, or any astronomy, for like the colors being as close as we can get, like representative color. This is representative sound.
all right.
Um,
I have another question
Go
that
for
I'd
it.
like to ask because it's something that has been asked of me before. So I'm going to throw it at you.
That's not fair.
And it basically goes like, does it bother you that 95% of the universe is unknown? We don't know
No.
what it is. We know that this is dark matter. We don't know what it is.
Yeah,
We know there's dark energy in it. We don't know what it is.
yeah.
How do you deal with the philosophical problems there inherent
Uh,
in that?
Very nice question. Thank you very much for this opportunity. Uh, I did. It does not bother me at all. I tell you, it does not bother me at all. And I think it's good that we don't know everything about our universe because we still have jobs. Apart from that, I think even if we discover what it is, and yeah, because there are groups that actively trying to detect dark matter, or somehow detect dark energy through clusters. I think Euclid is one of them, right?
Euclid and Roman are both working on dark energy.
Yeah. And there are also radio projects that are working on detecting dark matter, or at least to understand what dark matter is made of. I think, sorry, I lost my train of thought. I think even if we manage to find it, there's going to be something next that we will still, there is always going to be something new to discover. I don't think this will be the end. So I'm not so worried philosophically, because I don't think we will ever be satisfied that we know everything. And that's the beauty of being human. If we knew everything, it would be such a boring life. Yeah.
As I like to say, if we knew the answers, it wouldn't be research. If we
Yes.
knew what we were talking about, it wouldn't be research.
Yes.
Um, I'll add one little thing that I like to add in my response to that
Yeah.
is that dark matter doesn't bother me because it's gravity, right? And we understand gravity and we can see the effects of it, even if we don't know what it is. But dark matter and the accelerating expansion of the universe, we don't truly understand the physics behind it, and that's the only thing that bothers me,
Okay.
is that not understanding the physics. I mean, I'm comfortable with being ignorant. Okay, the smarter you get about the universe, the more you realize what you don't know. So I'm okay with being ignorant, but it's that missing physics that is what bothers me a little bit. Grant, what do you think?
oh yeah, absolutely. The only time you should be worried is when you think you know what it is. Like, the whole idea of science is finding out what you don't know. And the more you learn, the more you realize you don't know.
Okay, we got another question from the chat.
Yes, absolutely. Um, do the radio galaxy emissions give any indication about the rate of expansion, and are they shifted depending on their distance?
Uh, can you repeat? If they give an indication about the expansion of the universe?
Yeah, so this question is asking about the radio galaxy emissions.
Yes.
Do they give any indication to something like the Hubble constant, like the rate of
Uh,
expansion of the universe, and are they shifted depending on their distance? Is that measurable? Is that something you can
yes.
use?
I'm not aware of something like that. that we use radio.
Oh, there's the basics of getting just the redshift of the radio galaxies, which you can get, right?
The redshift of the radio galaxy you cannot get because radio doesn't give you a redshift, and that's the biggest problem. That's why we need other wavelengths. We need the optical association. That's why we do in our citizen science project, as I demonstrated. You have to overlay two images, one of the optical sky or infrared sky and one of the radio sky, because you don't know where this emission, the radio emission, is coming from. The only way to know is if you have association. If you have an optical galaxy and then jets coming out of it, you are 99.9% certain this might be the host, and then you get a redshift from spectroscopy. You know how far away the galaxy is. But
Yeah,
from
you
radio
showed
alone,
Hercules A in your talk,
yeah,
and there's an obvious elliptical galaxy at the center of Hercules A, right?
yeah. From the radio, you cannot get the distance of galaxies. And this is the biggest problem about the radio. And there was a very famous astronomer that said the radio is useless. I don't think so. Useless in the sense that you don't know how far away your galaxies are. You really need all the multi-wavelength information you can get and very high quality to be able to study them in whole. So I'm not aware of something like that.
Cool. All right, and I guess it's just because radio will have a broad spectrum of emissions.
Yes,
In a lot of the different types of Bremsstrahlung and other types of emissions
it
you get.
has. The one I showed, which is synchrotron from let's say megahertz to gigahertz, this kind of band. It lasts, so it also has to do with how long these sources live, because they are short-lived phenomena. The active galaxies live around 1 million to 10 million, 100 million years. So they're not that, and there is a cyclical phenomenon. Sometimes you have an active galaxy, it ejects the emission in jets and lobes. The activity in the supermassive black hole stops because there is no matter to feed it anymore. So this material fades away. But then something might restart the supermassive black hole. It starts fading again from dust, and then you have a new ejection of jets, and you can have a second active episode. But it's a very short-lived phenomena compared to galaxies in general.
So there's not like an Lyman alpha emission line that you can tag and go, okay, here's the red shift, or
No.
there's also the temporal component that comes on and off over the course of his life.
So here we're talking about continuum emission. It's not like an emission line. Of course, there is science in my brain, H2 emission, but this is not what we do in our project. We study the continuum emission so a wide band of emission from these objects that tells us about the physical processes related to the supermassive black hole or the active galaxy. But sometimes you also have emission from inside the cluster. This radio emission, and it's leftover electrons that somehow get accelerated by magnetic fields inside clusters. And then you have different phenomena, halos, something we are not dealing with in our project, but maybe some citizen scientist will discover.
All right, that sounds that is quite the problem for radio galaxies.
Yes.
Grant, what else have we got here?
So how has the launch and subsequent science operations of JWST affected your work? And where do you see it going with Nancy Grace Roman coming soon and the future projects to get you more of this multi-wavelength observation?
Yes, the better data we have for multi-wavelength data, the better for us to identify the radio sources. So there are a lot of radio surveys in the sky. In the southern sky, you have ASKAP. So for this one, we use the dark energy survey for the host, for the optical. For LOFAR, you use the northern skies. For the Cosmos, which I'm also a member of, the Cosmos Collaboration, the Cosmic Evolution Survey, we use everything that exists because it's a small patch equatorial, so it can be observed by both. I think the future is fantastic. James Webb data are unique. They showed us the universe at a very young age, and they're amazing discoveries. So, for example, currently in the Cosmos Collaboration, we're finding galaxies at redshift 12, redshift 13. It's unreal just to think about it. And we try to study galaxy evolution. So now it opened up a new window of galaxy populations when they're first being formed. You know, this is what we want to understand, how galaxies are formed and how we end up here. So the better data we get, multi-wavelength data, the better for the radio. But we also need to get better radio and multi-wavelength radio, because with one frequency, even if it's wideband, you don't get all the information. You need multi-frequency observations. ASKAP is currently doing that, EMU is doing that, LOFAR is doing that, and we're trying to combine for the same objects, for example, multi-frequency observations to study how this electron population that emits this synchrotron emission, how it ages, and this way to study the sources. So yeah, I'm looking forward to the new era of telescopes in general.
Yeah, the a friend of mine worked at the National Radio Astronomy Observatory here. And it was like we take images with multi-filters with Hubble and Webb, and we produce a beautiful color image and everything. But it was pointed out to me that, oh yeah, but that takes so much longer in like using the VLA because you need to get it in the A configuration, in the B configuration, and in the C configuration. You've got to do all the various configurations of the dishes in order to get the multiple resolutions that you need to create a really cool image. And it really brought across to me that, wow, outreach in radio astronomy is significantly harder than it is in optical and infrared.
Yeah, it's almost also not so intuitive to understand what a radio galaxy is, because you need to know a bit more about the physics, whereas we are more used to what a galaxy looks like because we are part of our galaxy. We see the Andromeda galaxy image everywhere, you know. It's easier to communicate to the public what a galaxy is, but it's not so easy to do this for radio. And
Right.
we're trying to change that through this project, of course.
It's a difficult project because I can point behind me and go, oh, those are stars emitting, right? But you have to sit there and say, oh, well, those are electrons spinning around in magnetic fields that emit off radiation.
Yes.
It's not quite,
Yeah.
doesn't
Yes,
quite
yes.
jump into the head as easily.
And as you mentioned before in your presentation of our Aquari, we cannot get a video of the universe, right? When you see nearby objects that have this repetitive phenomena, or, you know, it's easier to monitor in our lifetime, you can make a movie with many observations. But with radio that lasts for 1 million years, you know, for a source to grow, we cannot we cannot take a video and show it to the public, and also with most phenomena in the universe. So it's very hard to communicate. But the good thing is that we have all the simulations, like the ones I showed, and many more that helps us communicate this and the processes that happen better, I hope.
All right, Grant, do we have one last question for our speaker? I see there's a little bit more recent chat.
Yeah, they're all about dark matter and black holes. Do we want to go there?
Wow, okay. Let's do it. Well,
Um,
I can see, I will see my limits. Let's,
You're in outreach. You know you're going to get a comment about black holes somewhere,
yes, I
pretty
was
much every
waiting for
talk.
aliens, but it didn't come.
No. We filter out those aliens questions.
So there have been some recent hype and articles and papers suggesting that black holes are actually producing dark matter. What are your comments and thoughts about that?
I have not heard of that. I'm sorry. I'm not aware of that.
I haven't seen this paper
No,
either,
no.
but I mean,
What do
the
you
fact
mean
that you
producing dark
I-
matter?
if black holes would be baryonic matter, and we've accounted for all the baryonic matter that can be, right? So the dark matter being, 5 times as massive as the baryonic matter. Actually, you should probably define baryonic matter for the audience, would you?
Baryonic matter is what I discussed before, is the
Yep.
visible matters, this 5% of the universe, the ingredients of the universe. And how do the ingredients of the universe come up? From our theories matched to the observations. And the observation that we have about the Big Bang is the cosmic microwave background. This is what helped us understand how the universe formed and what is it's made of.
Right.
But I haven't heard anything about black holes, but we know that our galaxies are embedded in dark matter halos. This is something we understand and we're trying to observe it, let's say, but we don't have an observational evidence. We have um, indirect
Right.
indications through the attraction, because
Right.
it's a gravitational force. Yeah. And we see it
Yeah.
in clusters of galaxies when they collide with each other. But when it comes to black holes, I'm sorry, I haven't heard that.
Yeah. And everything when we talk about black holes, they're made from baryonic matter.
Mm.
Right. So the fact that, the cosmic microwave background limits the amount of baryonic matter to this much, well, then there's still that much bigger piece of dark matter that can't be baryonic. So if I guess what I'm saying is if black holes are baryonic, they can't be the dark matter.
Mm.
Right. Stuff like that. All right. One last question from me. What is that chocolate that you love so much?
Ah, it's that's the best question. Okay, it's called Eon.
Okay.
Eon. It has almonds, and it's the best chocolate in Greece.
All right. Well,
Yes.
I told you before that my wife and I are thinking, we're planning our trips for the next 5 years, and Greece has been one of our destinations. So we will try and get over there and sample that chocolate. Just for the chocolate. That's all.
That's what. Yes, only chocolate. It's fantastic. I hope you enjoy it.
All right. Okay, so ladies and gentlemen, our talk next month on December 3rd, Hunting the Stellar Undead with Gregory Sivakov, not coming from Greece, but coming from Canada. So we got 2 international speakers in a row. Thank you all for watching and have a great day.
Thank you. Bye.
Okay, you're good.
All right, thank you.